All right, let's talk about something we all do, probably 100 times a day without even thinking about it. You pop open a terminal and you type ls. But have you ever really wondered what's going on under the hood? Well, today we're going to pull back that curtain. We're going to follow that tiny command on its wild journey deep into the Linux operating system. So this is the big question, right? From the exact moment your finger leaves that enter key, this whole cascade of events kicks off, and it all happens in like the blink of an eye. We're going to trace that journey step by step from your keyboard into the shell, down to the kernel, and all the way back to your screen.
And this is where it all starts. The familiar command prompt, that blinking cursor, just waiting. Our shell, which for most of us is probably bash, is sitting there, ready for instructions. We type those two little letters, ls, and hit enter. And that one single keystroke, well, that's the starting gun.
Okay, our command is officially on its adventure. What feels totally instant to us is actually this incredibly well-choreographed dance between all these different parts of the system. First things first, the shell has to figure out what on earth we're asking it to do. So the first character in our story is the shell itself. Think of it as the interpreter, the front desk manager. Its main job is to take our input, ls, and figure out where the actual instructions for that program live on the computer. And it has a very specific, logical way of doing this. So the shell has this little checklist it runs through. First, it asks itself, hey, is ls one of my special built-in commands? A command that I handle internally like cd for changing directories. For ls, the answer is a big nope. So it immediately moves on to step 2. Okay, then I gotta go find a program file named ls somewhere on this system. And this is how it finds it. It looks at this special environment variable called path. You can think of the path as the shell's address book. It's just a list of directories to check, in order. So it looks in /usr/bin. Not there, then it looks in /bin, and bingo! It finds our program, the actual executable file, sitting right there at /bin/ls. Awesome, now it knows what to run. Okay, so the shell found the program, but now it has a new problem. How does it run this program without, completely stopping its own job? If the shell just became the ls program, your terminal would be frozen until it finished. The solution to this is so elegant, it's really at the heart of how Linux works. It makes a clone. It does this using a special request to the kernel called fork. And fork does exactly what it sounds like. The shell process splits in two, creating a perfect, identical copy of itself. This new copy is called the child process, and the original shell is now the parent. The parent just chills out and waits. All the action is now with the child. This is so cool because it keeps our original shell totally free and ready for more work. Now for what is, honestly, the most dramatic part of the whole journey. This new child process, which, remember, is still a perfect clone of our shell, is about to perform a complete and total metamorphosis. Using another system call, this one called execveo, the child process performs a kind of self-transplant. It completely wipes its own memory and code and replaces it with the code from the /bin ls program we found earlier. Poof! It's not a shell anymore. It is the ls program, loaded into memory and ready to go. This two-step dance, fork then exec, is what makes Linux so powerful and flexible. So now our ls program is loaded and ready. The main event can finally begin. The Linux kernel, the real boss of the whole operating system, steps in. Think of the kernel as the stage manager, giving our program everything it needs to perform. So what is ls's job, really? When you boil it down, its to-do list is actually pretty simple. 1. Open the current directory. 2. Read the names of all the files and folders inside it. And 3. Write that list back to our screen. Simple, right? But to get that simple job done, the program can't just go poking around the hardware by itself. That would be chaos. It has to politely ask the kernel for help using those special requests we call system calls. So it uses opendir to say, hey kernel, can you please open this directory for me? Then it uses redir over and over to say, okay, what's the next file name? And finally, it uses the write system call to say, all right, I've got the list, please print this to the terminal. And that write call, that's the grand finale. All that work, the searching, the forking, the transforming, all the kernel requests, it all leads to this one final moment, showing you the result. And there it is, the reason we started this whole journey. A nice, clean list of our files and folders appears on the screen. Mission accomplished. The ls program did exactly what it was born to do. But wait, what happens next? Well, as soon as LS is done writing to the screen, its job is over. It exits, and that child process is completely destroyed. The original parent shell, which has been patiently waiting this whole time, gets the signal that its child is done, and it springs back to life, giving you a fresh new prompt ready for your next command. The whole cycle is complete. So let's wrap all of this into the perfect takeaway. If you're ever in a job interview and someone asks you to explain this right here is your gold-plated 30-second answer. It hits all the key points. Find it in the path, fork a new process, exec V to become the new program, the kernel runs it, it prints, and it exits. That's the whole story, right there. And that is the secret life of LS. It's pretty amazing, isn't it? What seems so simple is actually this beautiful, lightning-fast dance happening inside your computer. And you know what? This same fork and exit pattern is how almost every command you run works. It's fundamental. So with the journey of LS complete, that leaves just one question. Which command's secret life should we uncover next?